Hi and welcome. Thank you for joining our talk on detecting financial crime using an Azure Advanced Analytics platform and MLOps approach. My name is Lars Haringa. I'm a data scientist and joined today I am by my colleague Saman Amini, machine learning engineer. We work for ABN AMRO Bank in the Netherlands. Our talk is split in two equal parts. First, I will explain why and how we use machine learning to do transaction monitoring within our bank. Then at the halfway point, Saman would explain and demonstrate our MLOps setup to efficiently productionalize our solutions. Let's give you a bit of context first. ABN AMRO Bank is one of the 4 systemically important banks in the Netherlands. That means that a sizable share of the Dutch transactions, of all Dutch transactions, passes through our systems every day. And because we're a financial institution, we're strictly regulated. So one of the regulations that we have to abide by is a legal obligation to do transaction monitoring. This means, in effect, that all the transactions that all the clients of the bank do, they have to be scanned and analyzed and sometimes passed along for investigation. And in some cases, that's the purpose of it, when we see something unusual or suspicious, we file a so-called suspicious activity report to the authorities. And this helps the authorities build cases against organized crime, for example. And banks are obliged to do so because they have a unique position, having access to all this transaction data. As you can imagine, especially the manual work of investigating these clients and transactions is a very costly operation. And it's not a secret that, for example, detecting financial crime employs thousands of employees, even for a bank in a small country like the Netherlands. Okay, so what is transaction monitoring and what does it traditionally look like? Well, we start with the source data, which consists of the transactions and maybe some client data, some information, whether we're dealing with an actual person or a business client, for example. And based on these transactions, we have a couple of rule-based triggers. For example, if you make some kind of a deposit of a substantial amount, we generate a trigger, an alert, and then this alert is passed on to an analyst in the operation who then investigates the activity of the client. And if this activity is deemed suspicious, they file a suspicious activity report, which is passed along to the authorities. Now, the point with this setup is that these triggers that generate, the rules that generate the triggers are hand-built, so they are a priori, and because of that, they're pretty simple. We usually only have a couple of them operating at the same time for the same scope. This, unfortunately, generates a lot of false positives, and a false positive is an analyst investigating something where nothing suspicious was going on in the end. So this is actually work that we prefer not to do. And an example of a simple business rule is a simple rule-based trigger is, if your deposit exceeds a certain threshold, we investigate. On the contrary, doing this with machine learning, transaction monitoring with machine learning, enables us to make hundreds of these kinds of decisions at the same time. This enables us to be much more efficient. So this TMML, transaction monitoring machine learning, I'll be using the term a lot more in this presentation. Okay, but before we can do this TMML, we actually need to have something in place to process our data, which is in our case we've chosen for a feature store. So this means that the transaction data and the client data gets processed in hundreds of different ways, thousands of different ways, to derive specific insights on these clients or transactions. Some obvious possibilities here is that we can have different categories of transactions and do volumes or aggregates based on that. We can look at periodicity. We can have an idea of what the expected behavior of a client is going to be and what would a deviation from expected behavior be. But also the client that a network that the client is actually engaged in is an important consideration. So not only your own bank account, but the information on the bank accounts that you do transactions with is very important in the context of organized crime, for example. So all of these insights are collected in this feature store concept, which is continuously refreshed based on the needs. So we need an IT platform that supports this kind of operation. So having this feature store alongside the rule-based system actually enables us to do our first example of machine learning. And this first example is actually a hybrid solution where we want to implement models. We've wanted to implement models alongside the status quo of this rule-based system. This model has been called, in our case, a hibernation model. So the purpose of this hibernation model is to take this flow of rule-based alerts coming from the rule-based system and actually drastically reduce the volume of this that has to be investigated by human analysts. And the reason we're able to do this is because this rule-based system has generated a lot of false positives in the past. So we use them as examples to learn from with machine learning. And once the rule-based system generates a new trigger that really looks like a false positive from the past, we say, no, that's not worthy of our time. We don't investigate those alerts. So with this setup, this was the first point where we've been able to talk about transaction monitoring, machine learning, optimizing the efficiency of this rule-based system. Okay, so in a nutshell, how did this work? Well, suppose in this case we have a two-dimensional feature space. The green crosses here are the false positives, and the red crosses are the ones that we actually have to report to the authorities. If we do a rule-based approach, we're only able to draw very crude decision boundaries. So here, it's become a triangle. We capture a couple of the red ones, but also a lot of the green ones. And the green ones are, superfluous. They are extra work. We actually don't want to do that work. We want to draw much more fine-grained decision boundaries, which is exactly what machine learning is able to do. So we're able to zoom into a much smaller area of this feature space, and also in different places in this feature space, much more detailed than we would be able to do using handcrafted decision boundaries. And the algorithm we've used in this case is an XGBoost algorithm, which is able to draw these abrupt decision boundaries on hundreds of features, doing cloud GPU training and inference. Small note on governance here. We're of course strictly regulated, so governance is always an aspect. As you can see in this illustration, we're actually missing one of the red crosses in the upper right of the triangle. So there is a trade-off always, even with the rule-based system, but especially relevant for governance in the context of machine learning. That if we're going to do this hibernation, we're going to miss some of the suspicious activity reports that we would have otherwise generated. So there's a trade-off to be made. As an example of how we do that in a bank, we've just formalized that trade-off. We've quantified it, and we've formalized it so we've called it the risk appetite. There's a certain appetite for exchanging missing a couple of these suspicious activity reports in trade for a much more efficient transaction monitoring operation, which is then able to focus its efforts on other parts of the feature space that may otherwise be unexplored. Okay, so this works pretty well. Let's do more of this. Second use case I want to illustrate here is next to the hibernation model, a recognition model. So again, using the feature store and actually using a lot of overlapping features from the hibernation model, we have a second model, dubbed our recognition model, which is actually trained on the same data, but with a different focus. And the focus is now not the false positives, but it's actually the suspicious activity reports, the actual suspicious activity reports from the past. And what we found here is that this model, taking into account these hundreds of features, is actually able to detect new alerts outside of the domain of the rule-based system that very often lead to SAR filings as well, to suspicious activity reports. So what we've actually finding here is that this rule-based system, the limitations of these crude decision boundaries, actually entice that we miss suspicious behavior that the bank should report. Now, this recognition model has a very high hit rate, so we're very satisfied with its performance. And as you can see, this actually increases the workload, but it also makes the use case here for using machine learning to do transaction monitoring rather than relying on, let's say, a previous generation approach. Okay, so for both of these models, we've used supervised learning. Small drawback, or big drawback, depending on for which department you work, is that supervised learning is always based on existing labels. And existing labels, you can think about that as knowledge from the past. So this hibernation model is only able to hibernate false positives that we've seen before. This recognition model is only able to detect suspicious behavior that we've seen before. Now, this is seen as a risk in bank terminology. And in order to mitigate that risk, we have a third model in this TMML setup, which is an anomaly detection model. Now, the idea of an anomaly detection model in general is that rather than using examples from the past, this anomaly model actually starts comparing the data to each other in order to try to find the ones that are most anomalous, the ones that really stand out. So if you visualize that, you can think about that. Again, in the two-dimensional feature space here, we have two clusters of data. Some of the data points, well, most of the data points are somewhat concentrated at the two, let's say, means. And we've put a red circle around the ones that are, furthest apart from one of these means. So you can think about those as outliers, or different terminology, anomalies. Now, the interesting perspective here is that with an anomaly model, we're actually able to detect instances that we've not that are outside of the scope of these existing labels. So an anomaly detection model is really able to do more of an exploratory monitoring on the clients. Of course, this is a bit more challenging than supervised learning, because we don't have these examples from the past to learn from. So now it becomes very important to rely on the features we select from the feature store, because those in the end determine what is deemed an anomaly and what's not. So here we're focusing on features that are able to describe clients as normal versus what we would deem suspicious in the context of money laundering. And this selection of features is, of course, informed by the money laundering patterns that we already know of. So there is some prior knowledge in this feature space, of course. A little bit of a technical detail, because anomaly detection is a bit harder than supervised learning. We actually use 3 different models for this approach, and we just average them together in an ensemble. So each of those 3 models, they have their own particular strengths and weaknesses. But the idea here is that if there's sufficient consistency among those 3 models, or maybe among 2 of them at least, then we have a good idea that the anomaly that we're detecting is an actual anomaly and not just a fluke of this particular submodel. And we have empirical verification here. So this model runs in production, it generates alerts, it generates SAR findings, and these SAR findings, the hit rate is the retrospective justification of running this model. But we also do additional research on these particular SAR findings to see if we're actually identifying new kinds of money laundering that are not already there in the rule-based system. Okay, so results. Well, as you can imagine, the false positive reduction is actually reducing the workload on the analysts. It's reducing the workload a lot more than the increase in alerts from the recognition and the anomaly models. So that's good. So the net result is a cost reduction on the operation, but another net result is that we're actually reporting more suspicious activity reports than we did before. So the bank has also become more vigilant. And this is really important because, well, for the false positive reduction, we need the capacity of these analysts elsewhere. We don't need that to investigate unnecessary false positives. It also saves these analysts unrewarding and repetitive work. And they actually need exposure to actual suspicious behavior in order to develop and become better analysts. At the same time, the bank has increased its own vigilance. So with this recognition model, we extrapolate the existing knowledge of SAR filings to beyond the domain of the rule-based system. And the anomaly model expands our understanding of suspicious behavior even further. And in terms of business value, what we found is that this TMML use case alone, the impact it makes on the operation is actually enough to support the data science and developer teams that are necessary to maintain this solution and more. So in terms of business value, is also a really important use case for us. Okay, let's also have a quick look on the continuous retraining. So our idea is that we want to retrain these models as often as possible, as often as makes sense in production, in order for us to take these new false positives that come from the operation and put them back into the hibernation model and make sure that we're as tight as possible and generate as least false positives as possible. So that means that this rule-based system together with the hibernation system is kind of a self-correcting system. If the rule-based system starts to generate more false positives, they will feed back into the hibernation models and increasing the hibernation rates. And the same thing is happening with the new SAR findings that are found from the recognition model and the anomaly model. Those are fed back into the recognition model. So if the anomaly model is, let's say, surprised by unusual behavior, which actually leads to a SAR finding, then the recognition model is going to remember those cases as well and be more vigilant to those as well into the future. And having these surprises feed back into memory to do recognition into the future, is that maybe even a form of, dare I say it, artificial intelligence? Well, anyway, in order for us to have solutions like this in production in a strongly regulated environment, we need to do a lot of monitoring, including feature-driven model behavior. And a lot of that is standardized. So it's good for us to have a framework that actually implements this automatically. A particular example of this in the context of bank-style governance is actually model validation, which operates on each newly retrained model. So model validation is actually a fully independent team that extensively checks model methodology and implementation, and they themselves are also audited again. So we really need these processes to be optimized if we don't want to fill our days bureaucratically. Now, currently, there are actually dozens more models either in production or being productionalized. And from our current and future projects, we have many needs, governance-wise, but also the need to keep demonstrating substantial impact to a somewhat traditional business-driven organization. For this, we've chosen to implement MLOps. And here to tell you all about it is my trusted colleague, machine learning engineer, Saman Amini.
Hi, thank you all for tuning in. This is Saman Amini. I'm a machine learning engineer within Detecting Financial Crime Unit at ABN AMRO Bank in the Netherlands. From here on, I'll take over from my colleague Lars, and I will be talking about MLOps principles and how we have brought these principles into practice. But first, I'll give a brief introduction about MLOps principles. Not that long ago, data science was perceived as a purely scientific field. And then it slowly got adopted into businesses, initially to experiment. For instance, companies would hire a few data scientists to see whether they can actually gain some insight from the data that they've been sitting on for years. Luckily for us, the result of many of these data science initiatives were quite positive, and that's when companies decided to actually bring these models into production. Now, the field of data science and machine learning has become very mature and also accessible. And probably developing a machine learning model does not take a very long time. But the challenge is actually bringing these models into production. Not only that, but also keeping them in production so that they can deliver the business value that they were initially promised. So probably you have seen a lot of stories like this where it took a very short time to develop the machine learning model itself, but very long in order to bring this model into production. And sometimes it actually never reached that far. So now we know that there are clearly some challenges that need to be addressed. In this slide, I've listed a few of these challenges. The first one is lack of a suitable infrastructure, an infrastructure that is easy to use and also covers all the needs of both data scientists and IT engineers. A second one is lack of a simple central model registry. Usually the end result of a model is a training pipeline is a model, usually in the form of a pickle file. And not having a model registry to version your model is and has been a challenge. The next one is alignment between IT engineers and data scientists. Usually these teams are completely isolated from each other and they even speak a different language. The next one is lack of a multidisciplinary team. And that's just a reality. We cannot fully rely on data scientists to productionalize machine learning models. Next to data scientists, you would probably need data and ML engineers to actually bring models into production. Next one is versioning and reproducibility, and this is particularly important for some sectors like the financial sector, in which you want to be able to know exactly which version of your code and data was used for making a specific version of your model. The next one is feedback and iteration. So once you bring a model in production, that's not the end of the story usually, because you basically want to keep monitoring and keep looking at the performance of your model in production. And so that if there is a performance decay, you want to go back and probably retrain a new model using new incoming data. And finally, sharing and reusing features. And this is important, especially if you are dealing with many machine learning models and you also have a large data science team. So now some of these challenges are very specific to machine learning and data science, but some of them are not that new, and there have been similar challenges in similar fields like software engineering and software development. And historically, there was always a gap between developers and operations. And in the past, if you were lucky, you could maybe have 2 or 3 releases per year. And not that long ago, a bit more than 10 years ago, DevOps principles were introduced to fill in that gap between developers and operation teams. And these principles are very simple and are as follow. The first one is fast flow from development to operations. Second one is shorten and amplify feedback between teams. And lastly, foster a culture of continual experimentation and learning. And in essence, MLOps is basically applying these principles to data science and machine learning. So MLOps is an agile ML engineering approach inspired by DevOps principles. It is an approach in which a multidisciplinary team develops and operationalizes machine learning solutions based on code, data, and models in small increments. And it is fully automated deployment of ML models into production. And finally, it is reproducible and reliable workflows. So why did we adopt MLOps? As Lars pointed out, we're dealing with many machine learning models, and productionizing this increasing number of models without having a standardized framework was becoming very challenging. Not only that, but also retraining and monitoring existing models in production became a burden and a bottleneck for our data scientists. And finally, lack of a framework to implement organizational quality gates and quality checks. Now, if you look at the typical flow of a model development and serving, it usually starts with business understanding and also data understanding to see whether you can actually answer a business challenge, tackle a business challenge given the data set that you have. And usually you go back and forth between these 2 steps. And next you go into more model development steps such as data preparation, modeling, evaluation. And once, as a data scientist, you are happy with the performance of your model, then that model goes into serving to users and clients. And ideally, you also want to have a monitoring feature that you can basically monitor the performance of your models in production, so that if there is a specific, if there is a decay in the performance of your model, you want to go back to maybe your data or even to your algorithm to fine tune and maybe use new incoming data to train a new machine learning model. Now, before getting into details of the one of the solutions that we came up with, I would like to introduce you to the tech stack that we're using. So basically, we are using Databricks, and within Databricks, we use different functionalities such as notebooks, clusters, repos, and Spark functionalities. And we also use MLflow integrated within Databricks. We use Azure repos for version control, our code base, and Azure pipelines for automated build and deploy pipelines. And for our feature store implementation, we use Azure Data Lake Storage Gen 2 and Delta Lake. And finally, we use Azure Data Factory for orchestrating data movement and transforming data at scale. And now let's dive into one of the solutions that could address productionalization of machine learning models. So for instance, you could have an exploration environment in which data scientists can develop their models. And in such an environment, you want your data scientists to have access to different sources of data. And what they can do is basically create features that would potentially be used in a specific model. And this feature definition and feature creation, in our case, is developed in a framework that is provided by our data engineers. And then the features then that when they are in our feature store, they can be used in the training step. And the idea behind this feature store is that it's model agnostic, so the features can be easily reused and shared across many different models and even different data science teams. And then within this very same environment, in this exploration environment, data scientists are capable of actually tracking their experiments inside MLflow, and they can also register their final model into the model registry. And usually you also have a model evaluation step in which data scientists look at the performance of their model. And in some cases, they want to even go back to the feature definition or even fine-tuning the training pipeline. So once data scientists are satisfied with the training pipeline in the exploration environment, we move on to the DTAP environments. And the difference between the DTAP environment and the exploration environment is really minor. The difference is that our data engineers and ML engineers would basically productionalize the code, and some of the things that we do on top of what data scientists build is writing unit tests, functional acceptance tests, and design automated pipelines to basically trigger training pipelines into our different environments. And the end result is basically in the production environment would be a model that is logged in the central model registry that could potentially be used by different teams for inference. So basically, they could make predictions based on new incoming data from feature store and send out these predictions to different systems within the bank. And ideally, you also want to have a monitoring feature that you can monitor the performance of your models in production and also monitor the distribution of new incoming data so that if there is a feature drift, you want to be able to detect that and also possibly go back and do a new retraining based on new incoming data. Now, if you look at this chart, you can actually easily see that by applying these MLOps principles, we have addressed some of the challenges that I initially pointed out. So now I would like to further focus on the training part, in which we have developed some sort of a lightweight framework for our data scientists to work on. This lightweight framework is basically it's a class-based design framework in which it consists of the regular steps that go into developing a specific machine learning model. And those are as follows. For instance, you have data extraction, data preparation, data monitoring, and so on and so forth. And data scientists can easily make use of the available functionalities that we have provided in these classes, or they can override these functionalities to make it more specific to a specific model that they're working on. And for deploying and submitting these jobs into Databricks, we use DBX. DBX is a command line interface tool for Databricks that you can easily submit jobs locally, but also easily you can integrate it within your CI/CD pipelines. And based on DBX, you can also specify entry points in which you can basically stick different steps of your training pipeline together. You can have one entry point to stick all the steps together, or you can have as many entry points as you want. So for instance, in this case, I have two entry points, one specific to my data preparation steps and one specific to my model training. And finally, we have also the build and deploy YAML pipelines, in which upon a push to a specific repository, these pipelines get automatically triggered, and in the build pipeline, test and quality checks are done, and finally in the deploy pipeline, a specific training job is executed in Databricks, and the final result would be a pickle file in a central model registry. And next, I would like to show a very short demo based on a dummy model with dummy data. The case is very simple. What we want to do is basically predict the type of wine, whether it's white or red wine, based on some physiochemical properties of the wine itself. And I show you how you can use DBX to locally submit a job to a Databricks cluster, but also you can make use of this DBX in your CI/CD pipeline to make it fully automated. So here you can see that within wine model subfolder, we have an entry point, and within entry point, we have imported some basic functionalities from the template that ML engineers have built. And on top of that, you can also have model-specific implementation. In this case, we have wine preprocessor, wine model evaluation, wine model wrapper. And then you can specify a training job class inside your entry point, and within that you can have a launch method. And then within this launch, you can basically stick different steps to each other. Here we set up an MLflow experiment and run. And within this, you can run, for instance, data extraction, data pre-processing, data monitoring, training, and so on and so forth. In this case, I have made some small changes, and I would like to test this out against a specific Databricks cluster. As you can see, I'm just simply executing this launch method from job class. So as I mentioned, we use DBX, and for using DBX, you need a deployment.json file in which you specify the number of jobs that you want to execute. In this case, we have one job called training_job. Here we specify the entry point and some additional parameters. The two commands that you basically use for deploying a specific job into a Databricks cluster locally. The first one is dbx deploy, and then you specify the name of the job. In this case, is trading_job, and there are multiple other arguments. In this case, I want to only upload my files to Databricks in this case. What this command does, it basically creates a wheel file for your package, and it puts these files on a Databricks dbfs location. The next command is dbx launch. You provide the training job name, as mentioned earlier. In this case, is training_job. The next argument is as -run-submit. Basically, as long as you submit the job, then it will start running the job on the cluster. And you also want to trace this job until it's finished. Once you execute this command, it also gives you a URL in which you can go and look at the logs and see what is happening. But here also you can see some basic logging. So for instance, right now it's installing the libraries. Takes some time until it's all installed and it runs the actual training job itself. Now you see that the job is successfully finished, and you can basically go up and log into that specific Databricks URL, and it will redirect you to the logs of that specific cluster, and you can also look at the experiment that has been logged into MLflow. You can see that one experiment was just added, one run was just added to this specific experiment. As you can see, with all the parameters and metrics logged into MLflow, as well as the all the artifacts that were logged in the training pipeline. As you can see, the model is also registered. Next is integrating these dbx commands inside your YAML pipelines. And you can see we basically execute the same commands. We give Databricks token and a specific host. And this can be also environment specific. You can easily make this available to your different DTAP environments. And once you push this into a repository, this CI/CD pipeline on Azure DevOps will get triggered automatically, and all the steps are executed. Then again, you can look at the logs of that cluster and also look at the run that was just added to this specific experiment recently using the CI/CD pipeline. And as you can see, an additional model was logged into the central model registry. And so now with that, briefly showed you how you can easily use DBX for deploying jobs locally, and not only that, but also integrating it easily inside your CI/CD pipelines. So I hope I could show you by applying these MLOps principles, you can easily standardize model development. You can standardize quality checks by basically setting up these automated pipelines, and built-in reproducibility. You don't really have to do much about it. As long as you apply these principles, reproducibility is built into it. The same thing with built-in traceability. Automated retraining would become possible. And then you can also have semi-automated monitoring, built-in quality assurance, and centralized model management for your pickle files. And finally, faster productionization so that data scientists can actually focus on more challenging tasks than retraining and monitoring the performance of their models manually. And with that, I would like to wrap up this session, and I would like to thank you all for your attention, and we'd be very happy to answer your questions. Feel free to reach out to us. Thank you very much.